We'll kick off the afternoon session with Marin Bukov talking about pre-thermal discrete time crystalline order.
Thanks, Harijit, and thanks for the organizers for inviting me to present some of our recent work. What I'm going to talk about is a rather, by now I'd say, old topic, discrete time crystals, but I want to show you some recent developments in how one can improve the observation techniques, and also, some of the first platforms that have been used, to experimentally realize discrete time crystals can now also be improved in order to continuously observe this, let's say, phase of matter. So this is a collaboration with Ashoka Joy's group at UC Berkeley, and I'm going to be mostly showing experimental data. I will hope that I'm going to be able to answer all your questions regarding this data, and I will try to be honest whenever I just don't know, because I didn't do this experiment myself. But what we did together with Christoph Fleckenstein is the theory behind that. All right, so let's get started. So first, I want to introduce the system of nitrogen vacancy centers, and then in particular, the technique of how to continuously observe the spins of the system. This is going to naturally lead us to the phenomenon of prethermalization without temperature that I'd like to briefly recap. And then from there, after a short recap of discrete time crystalline order, I'm going to be able to tell you exactly how one can use prethermalization in order to induce DTC order in such a system in a way that we can continuously monitor it in time. We'll then discuss the phase diagram of the system and the heating analysis and the meltdown of the order. So that's the menu for this talk. I'd like to start first by introducing the system of interest. So imagine that you have a piece of diamond. If you actually look inside it, what you'll find is a bunch of carbon atoms, and these are mostly going to be carbon-12 atoms. And carbon-12 atoms are such that they have no nuclear spin. But every now and then on this diamond lattice, you're going to have sites with carbon-13 atoms, and they actually carry nuclear spin. And these are going to be the protagonists in our system. But besides carbon atoms, you can also have so-called nitrogen vacancy defects, like the one shown here. What you have is, a dipolar spin-spin interaction between the carbon atoms and also between the carbon and the nitrogen atoms. But it so happens that the gyromagnetic ratio of the nuclear spins is quite a bit smaller than the gyromagnetic ratio of the electronic spins in the NV defect. And so it's very difficult to address directly the nuclear spins. And so what one uses instead in these platforms is we're going to use the NV center in order to transfer polarization. So we're going to shine a laser addressing the electron in the NV center, and we're going to transfer this polarization to the neighboring carbon-13 spins. And so in this sense, we're going to be able to prepare the system of carbon spins, essentially nuclear spins in a given state, and we're going to study its dynamics. Now, what you, however, want is you want to get rid afterwards of the NV, and one way to do this, and also a way to access the energy scales of the nuclear spins, is to apply a large magnetic field. So the first thing that this does is, of course, it sets the quantization axis. In this case, it's going to be the z-axis. And then what you can do in theory is you can apply the rotating wave approximation in order to eliminate this large energy scale, at the expense of addressing the low energy physics of the nuclear spin. So by doing this now, the NV is out of the game. And what we have now is a system described by the following Hamiltonian. It has two constituents. The first one is, and most important one, is a dipole-dipole interaction term, as you can see here. So this is a directional long-range interaction. But then what you also have is a leftover of this large Z field after you do the rotating wave approximation, is this on-site disordered term. Of course, we're going to be modeling the CJ terms as random numbers. They come essentially from the interaction between the carbon-13 spins and the electronic spins in the NV. But so these are going to be like random numbers, but they're going to be small, and we're not going to be talking about localization physics here. They're just present there. And I already mentioned, we have a long-range interaction. So, of course, in diamond, you don't have just a single such NV center. You have many, many of those. And these type of systems then only have access in experiments to a global magnetization. And as such, they're going to be actually measuring, the magnetization over a number of these centers in diamond. I mean, centers and their surroundings actually in the diamond. And so it makes sense if you see later on, a quantity called J, then that's just the average interaction, over many of these NV regions, and it's actually extracted from, some decay time. Okay, so that's the system of interest. Now, because we apply a very strong Zeeman field, we actually cannot measure the magnetization in the Z direction in this setup. And we can only measure the global magnetization of the system in the XY plane. So that's what's shown here in the system. So in the experiment, we have access to the XY magnetization, and it comes in the form of a complex signal, which has an amplitude, which is denoted by signal, and then a phase. And of course, in order to determine the phase, you would have to do some unwrapping of that signal. So let's now imagine that you take this system and then you hyperpolarize the spin. So you prepare a Z-polarized initial state in the nuclear spins. As I said, you cannot measure it. So in order to access it, what you have to do first is you have to apply a pi-half pulse and tip it over in the XY plane. And then you can actually do this sensing technique. So you can think of this sensing, by the way, as some sort of a weak measurement technique. And you can do it continuously in time. So this is to be denoted here. So you prepare the Z-polarized state, you do a pi-half pulse, and then let's say that we measure, in the XY plane. So what I'm showing you here is the amplitude or the signal as a function of time, which is normalized. And what you see is that it decays immediately in time, basically. This is because the Hamiltonian is three-dimensional, long-range interacting ergodic system. And you basically have no reason to believe that, the system would preserve its state. And trivially, if you look at the phase, of course, you can choose the branch cut in such a way that this corresponds to phase of 0. So this is a problem because the lifetime of this state is actually very short. Now, in order to increase the lifetime of the state, what we do is a so-called spin locking technique. So this is just a periodic sequence of X pulses shown here in the picture. So on the X-axis is time, and then these are essentially the X pulses with period tau. The angle of the pulse is theta X. This sequence is essentially given by a unitary operator. If you apply this, n times, then you're going to get this product. I'm going to show you in the next slide how to compute an effective Hamiltonian, essentially, to describe this whole process. But importantly here is that in between these spin locking pulses, you can actually acquire signal from the system. So you can measure the system continuously up to the application of these strong kicks, because whenever you have a strong kick, then you assume that your Hamiltonian is basically off to very good approximation. So no, you don't reinitialize, and that's the actual, yes, and that's going to be part of the novelty here, basically, in this experiment. So you don't have to restart your experiment. You just do one run, and as you go, you're sensing your global magnetization. If I was an experimentalist, I was able to give you like a more precise answer to this, but I think it's some sort of a weak measurement. Like that's the best I can. It's an ensemble measurement. There's some very small back action, which is essentially relevant to the system. Okay, but now this spin locking sequence has a degree of freedom, which is this angle theta, and of course you can study how much of your signal survives as you vary the angle theta here on the x-axis. You can hit some resonances at pi and 2 pi, so we want to stay away from those, right? We want to keep our system alive as long as possible. So we're going to choose from now on a theta angle of pi half, which is where the signal is maximal. So if you do that, then this is what you get. So this was like the previous data that I just showed you with a lifetime of 1.5 milliseconds. With this spin locking technique, you can actually get a 60,000 times longer lifetime. And then your lifetime then is a T2 star of 90 seconds here. So you can tremendously increase the lifetime of your system. Okay, so physically, basically 90 seconds in the lab. Okay, now in theory, we know how to think about this increase of lifetime due to periodic shaking. Essentially, what's going on here is the spin locking technique induces a quasi-conserved X polarization or X magnetization. And this is what essentially preserves the state for such a long time. So let me just tell you how that works in detail. So the mathematical machinery behind it is essentially the Tongling frame expansion. This is similar to the Floquet-Magnus expansion, but a little bit more general than it. So what you have here is you have this unitary that we defined on the previous slide. The idea is to find two leading order approximation in the pulse frequency tau, an effective average Hamiltonian. And so if you do the algebra, what you find is an average Hamiltonian that looks like the original dipole-dipole interaction, except now you get this additional YY term. And because of this, you can show, you can convince yourself that this Hamiltonian preserves the global X magnetization. If you consider higher order correction terms, then this is no longer the case. So this is a truly, prethermally conserved quantity. But nevertheless, and this is actually the reason why we observe the decay eventually at later times. But this is already, when tau is sufficiently small, it is already sufficient in order to stabilize this state, to, as I showed you, 60,000 times longer durations. So here's again the same data as before, shown. So again, the signal versus time. This is now shown on a log scale. These are the typical way to present this data to see a pre-thermal plateau. And again, you can kind of see if you don't do the spin locking, then you decay basically immediately. If you do that, then you get a couple of order of magnitudes higher lifetime. So how can you think about this theoretically? Let's initialize the system. So after we do like this pi-half pulse, I can assume that my system is given in a mixed state, which is a product state of all the spins. And there is a little bit of an X polarization, right, after the pi-half pulse. And now you can ask yourself the question, well, the long time state is going to be determined, using the eigenstate thermalization hypothesis. The temperature of that state should be determined by the energy density of my initial state. But if you compute the energy density of this initial state, you find 0. And that's already a little bit suspicious because whenever you have a state of 0 energy, then it lies in the middle of the spectrum. So it means that it's already infinite temperature to begin with. And now you have a state that's an infinite temperature. And the question is, why does it survive, right? So why doesn't it decay? And that's something that people, stumbled upon. Actually, it was motivated by a similar experiment in 2018. And then there was like a theory developed also by Wenwei here in the audience. This is a phenomenon known as prethermalization without temperature. This is because you already start at infinite temperature. It's a slightly different phenomenon. However, the state of the system is, or the polarization is indeed protected by this X quasi-conservation law. And this is induced by the spin locking drive. So at this stage, what we have is a long-lived prethermal plateau plus this ability to continuously monitor the system. And the question that arises here is, okay, what should we do with this system, right? Like if we have like these abilities. And what I want to show you next is that you can actually use these ingredients in order to engineer a prethermal discrete time crystalline order in this prethermal plateau. Okay, so before we go into this, let me just put some basics. This is a workshop on periodically driven systems, and in the first talk, we haven't seen Floquet's theorem, so I'd like to put it here. So if you have a time-dependent Hamiltonian, so a Hamiltonian which has this discrete time translation symmetry, then the unitary evolution operator, which in general is given by this time-ordered exponential, can be shown to factorize into a product of two other unitaries. There's the micromotion operator P of t, which inherits the same periodicity as the drive. There's this effective Floquet Hamiltonian, which governs the so-called stroboscopic dynamics of your system. So that's dynamics. If you look at the system stroboscopically, that is to say at integer multiples of the driving period. And what's important about this object is this effective Hamiltonian is actually time independent. So in some sense, these are systems that are resembling static systems, but not quite, because you have this additional structure here coming from the periodic drive, and you can actually use this structure in order to find states, to find order that doesn't exist in equilibrium. Let me show you how that works. So again, if we look at this unitary over one period, the micromotion operator goes away because it wraps back to the identity at integer multiples of t. So we're left with this object, the Floquet unitary. And the spectrum of this object is defined on the circle because it's a unitary operator. but the eigen phases can be distributed essentially in any way on the circle. Well, not quite in any way, depending on your system, right? There's some statistics that these numbers have to obey, but this is not so important for us right now. What is interesting now is that if your periodically driven system has an additional symmetry, so suppose that it has an additional Z2 symmetry, then you can actually induce some structure in this eigenphases spectrum. So let me show you an example of how that can work. So if you take a Floquet unitary, which consists again of two steps, one of them is your Hamiltonian, and the other one is a global X flip, then you can show that up to a static unitary transformation, this unitary can be decomposed into a product of this global X flip and e to the I of some static effective operator in such a way that this effective Hamiltonian commutes with the global X flip. And if that's the case, then your quasi-energy spectrum has to appear in pairs. And that's something that you can convince yourself. For instance, if you take a common eigenbasis of these two operators, and you say that this is an eigenbasis with eigenvalue En of the effective Hamiltonian and an eigenvalue P of the global X flip, which can only take the values plus minus 1, and then you plug it back in, then you'll convince yourself that all the phases are En plus minus I, and that's what you find here. Now, this is now interesting because, as you can see, in the spectrum of the Floquet unitary, you reflect basically two symmetries. The first symmetry is the Z2 symmetry, which is this pairing, together, however, with the time translation symmetry that allows you to talk about Floquet unitary in the first place. And so if you take any initial state which breaks this X flip symmetry, then this state necessarily also will break the time translation symmetry of your Hamiltonian. And therefore, observables will necessarily oscillate with a period 2t. So this is, I think, by now like old physics or physics of, I don't know, like 5 or 6 years. But such states are actually, easy to find also in our experiment. So one such state would be a state where you, start in the X direction, as I've shown you. This is actually feasible. Now, this breaking, the breaking of this symmetry leads to so-called time crystalline order. And this order appears, broadly speaking, in two flavors. So this can be either eigenstate order. For instance, if you have the system which is many-body localized, then this is a genuinely non-equilibrium order, and you have no notion of a temperature in this system because you don't have thermal equilibrium. But you can also have time crystalline order in a prethermal sense, in which case it is similar to equilibrium because we have like an effective Hamiltonian, right, in a prethermal plateau, and we can have the notion of temperature. So in this talk, I'm going to focus on the second class, which is the prethermal. Okay, so how do we now generate this additional Z2 symmetry in our system? So remember, what we need is we need the spin locking sequence here in order to stabilize the state first. And also, it allows us to monitor the state. Now, on top of this, but now the problem is that what we want to do is we want to apply these global X flips. But we can't just apply, the Z kicks because again, we have this strong Z field in strong field in the Z direction. So, the system wouldn't see actually any effect of the Z kicks. So what we will do is we will apply instead this X flip using Y kicks. So what you see here now is the actual sequence that we will apply, the total sequence to the system. We start with a state that's Z polarized, we flip it in the XY plane. And then we have this alternating sequence of a spin locking block and a Y rotation at an angle gamma, okay? So the total Floquet unitary now for our system includes, alternating sequence between this spin locking unitary and a global Y rotation at an angle gamma, and gamma is essentially a free parameter. So in some sense, this is a two frequency drive, even though you can play with these numbers m, which is the number of Floquet cycles, and this number n, which is the number of X kicks within the spin locking block. And depending on these two, you can basically vary. It's like having two different frequencies, even though these are pulses, so it's not continuous. Okay, so it's a little bit more complicated, but that's as hard as it gets. So from here on, we can basically see what we can do. So with this new sequence, right, can we see now where this Z2 symmetry will come from that we need? So yes, we can. In particular, you can carry out a calculation that simplifies a lot if you choose the angle gamma to be an integer multiple of pi. Then in this case, this whole unitary is essentially the same thing as two unitaries. So the first one gives you a kick, so basically a rotation about the y-axis with respect to this total angle, times another piece which is given by the by the average Hamiltonian plus an additional term in the x direction. And this average Hamiltonian is the same average Hamiltonian that we had from spin locking. Now, this extra term is a little bit annoying. So what we thought about is, can we actually get rid of it? And you can compute an expression for it. It's a little bit messy. But what you see immediately from here is that if you choose this L in addition to be odd, then this additional term goes away. And that's, the easiest way to think about our system. So in this case, the total Floquet unitary amounts to a global X flip and, another piece which evolves continuously with this average Hamiltonian. And in this case, we basically satisfy, like the conditions for this additional Z2 symmetry. By the way, you can also see that there is no additional unitary transformation that you have to take into account. This is only the case when you consider odd L. If you look at even L, then you have to work a little bit harder to see that. But essentially, you have a global X flip, which will commute with the effective Hamiltonian. That's something that you can convince yourself by just looking at this expression and sending IZ to minus IZ and IY to minus IY, and the SU2 term is anyway invariant. Okay, so let's see now how that works if we do this in an experiment. Okay, so first of all, if we set gamma to 0, right, then we're back to spin locking. So we recover what we had before. Now, if we set gamma to pi and we choose L to be odd, what you see here is the decay of the X magnetization as a function of time. And there are two axes. For the experimentalists, you can look up here. This is the time in actual seconds. Whereas for theorists, the better axis is essentially the lower one where we show the number of Floquet cycles. So again, one Floquet cycle is one of these spin locking blocks plus the kick, even though there are actually many more kicks here in between. And if you now look at these phases, remember one can also unwind the phase in this measurement that we do. And going back to Sarang's question, so this is now the measurement continuously in time without really doing a projected measurement and having to restart. And that's actually important to emphasize. Then if gamma is sufficiently close to pi, then you see in this phase signal essentially this positive and negative flipping that gives rise to the characteristic signature of the time translation symmetry breaking, time translation spacious symmetry breaking. Now, if you have a technique that allows you, with a single shot to basically, measure one such curve, then it's particularly easy to map out the phase diagram of this model. And that's what I want to do next. So what we see here now on the x-axis is this flip angle gamma. And on the y-axis, we have the time. So again, on the left, there's a Floquet cycle, and on the right, there's time. And the color bar here gives you the value of the X magnetization or the X polarization. And what you see here, once again, so what I showed you before on the previous slide were essentially two cuts, one close to gamma is equal to 0 and one close to gamma is equal to pi. But now we can basically repeat this for a bunch of values of gamma. And this is actually super easy to do apparently in this experiment because each one of these traces is a single run of the experiment. Okay, so back to the phase diagram. So in the vicinity of gamma, what you find is, like a boring prethermal phase without any additional order. Whereas if you go to the vicinity of pi or minus pi, that's the same. Then you find this alternating pattern. And the interesting thing is that this alternating pattern survives to a very long time. So you can go up to, like 100 and maybe 400 of those Floquet cycles. And I don't know if you can see that still, but in principle, there's still like a faint signal here. So this platform, using the spin locking actually allows you to achieve lifetimes of these time crystalline order that are competitive with all other platforms that have been used before, and in cases even better. So I want to show you basically a movie of the process data of how that works. So again, here you see the polarization as a function of the Floquet cycle now. And you see, as you vary the angle gamma, so as I'm doing basically a sweep here within like this, this black vertical line, you can see how essentially the signal changes. And you can also do this in the trivial phase, for as long as you go like not too far away into the time crystalline phase, then you have no sign flip whatsoever. Yes. Oh, so okay, so you mean this one here? So remember the plot that I showed you before, where you can hit resonances. So if you hit the resonance, so if basically you choose the angles in a non-particularly smart way, then you can hit resonances, and then your effective Hamiltonian is completely different. So it has nothing to do then with these quasi-conserved symmetry properties that you need in order to have that. And then what you see in the end is that this, grows in time, in a way that it actually, it melts. And we're going to come to the discussion on the melting in a second. Any other questions? Okay. Right. So let's now check. There's people that have been working in this field have come up with a number of criteria that you have to check, in order to say that you have actually a stable, proper time crystalline order. So the first one, of course, is a necessary condition, which is spatial temporal symmetry breaking. I think I'll convince you that this works out. Second thing that you want is a parametrically controllable lifetime of your prethermal crystal. Now, in our case, what we can play with is the duration here in between the X kicks within the spin locking sequence. And that's what's shown here, essentially, in both cases. On the X-axis, on the Y-axis, you see the lifetime. So as you make essentially the kicks faster and faster, then your lifetime goes up, and you can increase it roughly by 1 order of magnitude here. So definitely the lifetime of the time crystal is essentially under control. Then you also have to worry about sensitivity to initial state. So remember, you want to show that irrespective of which state you start from, for as long as it breaks the Z2 symmetry, you'll always see this pattern. Now, this is a little bit difficult in this system of NV platform, to cover large, different types of initial states. But what you can do, rather with ease, is you can change the hyperpolarization time. So remember, the way we were preparing this state is by, applying a laser to hyperpolarize the system with the help of the electron in the NV. And depending on how long you apply this for, you can change essentially the polarization of your state. So you can basically obtain a larger epsilon. And the different curves that you see here, colored by the hyperpolarization time, show you that different initial states, although still similar, but different initial states all behave essentially in the same way. So we also have sufficient insensitivity to the initial state. And the last and most important property is the robustness to small perturbations. So in order to check the robustness to small perturbations, what you can do is you can take one such time trace, and what you can compute is the discrete Fourier transform. So what you see here is the discrete Fourier transform of the X magnetization. So that's the color here on the color bar. On the X-axis, I have the same flip angle gamma. And on the Y-axis, I have this Fourier frequency omega. Okay, so now if you do have a time crystalline order, what you expect to see is this flat horizontal white blobs here, which essentially show you that your response is not only tied to a fixed frequency, but even if you vary the frequency a little bit, your system is still stable. So that's one of the necessary conditions again to see that. If you did not have interactions, then what you would have seen is actually this dashed cyan line here. So the presence of interactions is actually crucial in order to stabilize this point. And we also see this in the experiment. Okay, so this was all so far that I've shown like experimental data. So you might wonder, okay, so what did we actually do, on the theory side here so far? And I want to show that you can actually reproduce these dynamics using a rather simple simulation. So what we did is, okay, so we want to do exact dynamics because we need to reach very long times, and eventually the system will get entangled. The state will get entangled. This limits, the number of spins that we can simulate. We were able to push this to 16 spins. Now we cannot simulate, well, we didn't want to simulate because there was no need, a proper diamond lattice, because, there's, you cannot put like, 16 spins, we won't get like a proper structure there anyway. So what we decided to do is we took a random graph And on this random graph, the only condition that we made sure is we make sure that the spins are not too close and not too far away. Because if it happens that one spin is too far away, then it doesn't contribute to the dynamics, and essentially you're left with a system of 15 spins. You don't want to lose that. So exact diagonalization, exact simulation of 16 spins produced the following result here. So as you can see, as a mirror image, the agreement is really excellent. Of course, it's not perfect. If you look very closely, you'll see certain case, in certain parts, it doesn't really work so well. Also, in terms of the Fourier transform, the signal is a little bit, well, some patterns are a bit stronger, in the theory. Now, it's a little bit difficult to compare here because I'm only showing you, a color map, if you wish, of the diagram. So let's actually take cuts and see what happens if we do cuts. So these are now various cuts on the color bar here. I'm putting epsilon. So epsilon is essentially the deviation. So this is in the trivial phase, close to gamma is equal to 0. And I'm going to vary, how far away I get from 0. As you can see, in this case, the top line will be the theory and the bottom line will be the experiment. So this is, the decay of the magnetization as a function of time. And in all cases, you kind of see that the system decays. If epsilon is sufficiently small, then the prethermal plateau survives for longer, as you would expect. Now, in the vicinity of the time crystalline phase, you find the period doubling effect. So it's reproduced, qualitatively in a nice manner. And you can also do the same thing, for the signal only. And then you find, that the pi and the 0 regimes are essentially indistinguishable. You can only distinguish them if you look at the phase of the signal. Okay, so now in the last couple of slides, I want to discuss, how stable this prethermal plateau is and essentially what controls, its lifetime. And before we do this, we just need to remember that this total Floquet sequence actually consists of two sequences, right? There's a spin locking sequence, and then there's the actual Z2 sequence. So the spin locking sequence itself alone has a prethermal lifetime, or in other words, a heating rate, which I'm going to denote by gamma spin lock. And the heating rate of the spin locking sequence is determined by its intrinsic period here, tau. But then on top of this, you have these orange kicks, the Y kicks, and they're also going to contribute to the heating of your system. So you have to take into account these two possibilities. Another thing you have to keep in mind. So if you think about it, okay, people have discussed heating in periodically driven systems, and the common conception is that this heating should be exponentially suppressed. But if you actually look into the details, heating is exponentially suppressed for systems that are local and short-ranged, right? And our system is actually, okay, still local, but it's a long-range system. And the reason why the standard exponential suppression doesn't apply is because in the cases of long-range systems, you don't have Lieb-Robinson bounds, and so essentially you cannot do the argument. Having a dipolar interaction in 3 dimensions is actually a little bit more challenging because it turns out that this interaction is actually critical. What I mean by this is that if you try to compute the energy, just the energy of your Hamiltonian, for a large enough system, then you're going to end up having a logarithmic divergence. And so this essentially complicates further, the study of long-range interactions. I forgot to mention that long-range interactions, prethermalization of systems with long-range interactions have been studied before, but it's, this has been done away from, from the critical point. And critical prethermal time crystals have also been studied, I think, by Wenwei and Sun Won. In 2017. So the question is now, if you have this case and it's probably not exponential, but is it power law or is it something else, right? So how can you do that? Can you actually check, what the experimental data is giving you? So to this end, we decided to build, the simplest model we can come up with. So you consider 2 consecutive time steps, so stroboscopic time steps, and then the difference in the measured X polarization is essentially proportional to the polarization itself, and then it has a contribution, one coming from these 2 processes. So a contribution from the Y kicks and a contribution from the spin locks. And this is, it's already, this equation already captures, like the interesting limiting case in particular. If you set gamma is equal to 0, so you don't have the Z2 sequence, then the system will still decay with the spin locking rate, and also, the other way around. But now you have them both. you can, easily, turn this into a differential equation and then write down, heuristic exponential for the solution, and then you obtain a total, heating rate, or the inverse of it is a lifetime. That would be basically the inverse of this rate. And moreover, now what we can do is we can make an assumption for the scaling of the Z2 sequence to be like some power of epsilon. And the question is now, what is the experiment going to give us, right? In terms of lambda. So, not so surprising, what you find is Fermi's golden rule. So here on the left, I'm showing you the experimental data. So the way you do this in the experiment is you consider the lifetime. So you can, subtract. So you can independently measure the spin locking lifetime, and then you can subtract it away. And as you subtract away the spin locking lifetime, then the question is, if you plot this on a log, can you extract the power? And then if you do this, in the vicinity, well, essentially in the vicinity of the trivial phase, then you find lambda of 2.06. If you do it in the time crystalline phase, you find 2.21. So this is what we find in our experiment, but I want to point out like a recent paper by Chong Su, and in his group, they actually found a stretched exponential in a similar dipolar interacting system. So I wouldn't say that, like this really settles it, but it's, the question I think is largely open. So if you have like some ideas, how to compute or how to estimate like the heating rate in this critical regime, I'd be interested to hear them. What I want to mention as a take-home message here is that prethermalization doesn't really require an exponential lifetime, right? So in the end, what's more important, at least in my opinion, is that the duration of your prethermal plateau is actually controllable. So you have a parameter knob that you can tune, which allows you, to go to longer and longer times. And the reason why I'm saying this is because, in our experiment, we were able to reach about 400 Floquet cycles with a Fermi golden rule type of, duration for the prethermal plateau. And there are a lot of experiments on DTCs. They have, in theory, they have like an exponentially suppressed heating rate, and nonetheless, they cannot reach that long in time. So it really depends on the platform that you're actually looking at. So for any like practical or experimental purposes, what's more important is the controllability. Okay, and now towards the end, I'd like to just flash, some other regimes that we also have in this system. So so far, the regime that I showed you, from theory perspective is not so exciting. But what you can now do is you can study the interplay between M and N. So far, I've been using the regime where N, the spin locking sequence, contains 300 pulses before you actually apply one of these Z2 pulses. But what you can imagine now is that you put N and M roughly on equal footing. And if you do that, then you're actually going to get like new regimes, and not only new regimes, but also drastically different physics. What I'm showing you here is just the magnitude, so the absolute value of the X magnetization, again, against the angle. Once again, there are two phases. There's a trivial phase at 0, and then there's a time crystalline, let's maybe call it a time crystalline order, close to pi, right? But now you see, just by flipping N by one integer from 8 to 9, you completely change the stability diagram here. And this is because a single, basically, change of this integer by 1 changes the effective Hamiltonian of your system. So this is essentially how you see that. Nevertheless, if you do these cuts and you look in the vicinity of pi, in both cases you actually find the proper periodic, so the proper phase. So I think this shows you that these techniques, this technique of essentially using two different types of pulses that are concatenated and then you can play with, can actually give you interesting regimes that are inaccessible with single frequency drives. So this is still being explored, so it's currently in the output. Okay, so I got the notification by Arijit, so I guess I should wrap up. Just in summary, I want to say that we've developed a protocol for continuous observation of prethermal DTCs. It's continuous in a sense that it's done through a weak measurement, so we don't really have to stop the experiment and restart it. So you just go through. It makes use of a two-frequency drive. So first, you need a spin-locking drive to stabilize a quasi-conserved X polarization. So in some sense, you engineer, like your conserved quantity, And then you also engineer your symmetry, right? With your Z2 symmetry with the help of the drive. And then you break it and you see what happens. And it's important to mention that the lifetime of this plateau is, a golden rule lifetime, but nevertheless, you can actually reach state-of-the-art lifetimes of about 400 Cloquet cycles. Okay, so with this, I'd like to give you the floor for questions.
When you're talking about N versus M, so if you can go one slide behind. So what is the, okay, you've shown the rigidity in gamma, right? Pi plus epsilon. If you change epsilon by some time, you have some rigidity over there, right? What is the rigidity in time tau? So if you change the time between theta x pulses.
Yeah, so that was, a couple of slides back. So tau is something that, that we varied here, right? So if you change tau, then you actually control the duration of this prethermal plateau.
Right, but what I'm saying is, if let's say between each pulse there is some error between tau plus delta, something like that.
Oh, you mean that your pulses are not strictly periodic? So that's actually what's going on in the experiment, because in the experiment they do have imperfections. Because of this, this is tau up to the precision that they can do this, like within their pulse laser. But what I also want to say is that, you can also mimic this in theory. You can do that. And what you gain by doing this is you actually minimize finite size effects in your, small 16-site, simulation. So if you take just 16 spins and you fix tau, what can happen with your long time curve is that you're going to go through the prethermal plateau. And then instead of going to infinite temperature where you should have gone, you're going to get stuck at some finite energy density. At the moment you put a little bit of noise, but not too much, right? Then you're removing that. You're basically making the dynamics as ergodic as it can get.
Okay.
The only caveat with this is that if you actually choose too large of a deviation there, then if you're not careful, you might change the heating law, basically the scaling law. So you have to be really careful.
So does this explain N being 8 or 9? So interplay between N and M's, because now if there is an error in the gate, like in the pulse time, and now if you switch from N is equal to 8 to 9, that error is propagating more, right?
It's not sufficient to only explain N to M. So basically to see like the difference between N and M, you would have to mess up essentially with, with the rest of your Hamiltonian, right? So what I'm saying is there are additional terms in your effective Hamiltonian, and this is what brings, like the actual difference.
Thank you.
Is there a way to estimate experimentally how many spins contribute to
yes,
this time?
There is, and I should have mentioned this probably. So it's between 1,000 and 10,000. It's really a rough estimate, but yes. And this is, 1,000 and 10,000, for a single NV center, right? Like then on top you have like multiple of those centers, in your diamond. It's like an ensemble of those that you measure in the end.
So how robust is this to, like, let's say changes in the power law of the interaction? Like if I have Ri minus Rj to the power 3 plus delta, will these things work or?
So, okay, we didn't check explicitly, but I can speculate. So if you choose the power in such a way that you make the system effectively short range interacting, then I would expect, by the theorem that I mentioned, that you would find, an exponentially long-lived, prethermal plateau. On the other hand, if you make the system longer range interacting, then it's going to heat up faster. But in this case, I don't expect to have any further change. I do think that Fermi's golden rule will persist there. And there is a paper actually that investigates this by Francisco Machado in Norm Yao's group. Yeah, here, this one, where they've actually studied, prethermalization as a function of this alpha parameter in the interaction strength.
I have one more question. So in the experiment, you said this is continuously monitored, right? And it's not like
it's continuously monitored in between, the spin locking pulses. You cannot monitor during the application next pulse because this is too strong.
Yeah, but in the theory, you never did any kind of, let's say, continuous monitoring theory or anything.
In theory, we monitor, we cheat because we can, I have the state of my system at any point in time, right? And
okay, but I mean, do you have any idea why this thing does, like, I mean, usually when people think of continuous monitoring, it sometimes changes the dynamics, right? But do you have?
Yeah, so the question is, why the back action is sufficiently small,
Yeah.
right? So I don't have an answer, good answer to this. Like this goes back to Sarang's question, right? So what's actually going on, like in this back action? So that's
some channel that you're applying, and that just adds to your rate, the decay rate.
it could be. It might be. I need to think more about that. I see nothing against it.
No more questions. Let's thank Marin again.